Today we're going to look at a very quick way to convert between polar and rectangular form for complex numbers. And this makes use of just one geometric observation, and it is the following one. If you know Argon's diagram, and you definitely have seen it before, it's the one on which we represent a complex number in terms of its real and imaginary part on the x and y axis. You can use the rectangular form to identify A, real part, and B, the imaginary part on this diagram. So you have A and B there, and you can join them to draw the vector that represents our complex number. Now that vector is described by Z in terms of its coordinates A and B, the real and imaginary number. By looking at that diagram though, we see straight away that there is an alternative representation in terms of the length of the vector and the angle that it makes with the x-axis. So rather than describing it by its x and y components, a and b, the real imaginary part, we could describe the same vector and it would be uniquely determined by just giving r the distance from the origin or the length of the vector and theta, the angle that it makes with the x-axis. So we have a way to move between r theta, a and b, and r theta, and vice versa. How do we find the formula that we can apply quickly to describe these changes, whether we start from AB or R theta and we want to find the other representation? Well, they will be very, very easy to derive if we have a look at this triangle. The triangle is the following one. If we use OAZ, I'm going to report it here. We see that this is a right angle because it's the one between the x and y axis. This is theta, this is r, this is b, and this is a. So I've just represented this triangle here in a much larger version, well, a slightly larger version. Okay, so we see straight away that from this triangle we can derive some useful relationship. First of all, r is related to b and a through Pythagoras theorem, which tells me that a squared plus b squared square rooted is equal to r. And also that the tangent of theta, we know that this angle here is such that the tangent of theta is equal to b divided by a. And we can invert that to find that theta is equal to the inverse tangent. So I'm inverting the previous formula of b over a. And this gives us already two relationships that we can use. And in particular, if you look carefully, these two relationships allow us to convert from a, b to r theta. So from rectangular to polar form. Similarly, we can write down two relationships that connect r, b, and a explicitly through theta. And these are the following ones. So if we look at r, we see that a is equal to r cosine of theta, because theta is the adjacent angle to a. And b is equal to r sine of theta. And this is another trigonometric relationship that is true because b is the opposite side to theta. And therefore, here we found relations that connect r theta and a and b in such a way that we can easily move from r theta to a b. So it's not necessary to remember Euler's formula and substitute in and recognize what theta is. These are two, actually four, quick formula that you can remember straight away. And if you don't even use this triangle, to move from r cos, so from r theta, so the polar description of a complex number, to a and b, real and imaginary part, rectangular form of a complex number. So if you know theta and r, you can insert them in this formula to get a and b. And if you got a and b, you can find r and theta by using this set of formula. I hope you enjoyed that and you will use it in your problems straight away. Thanks for watching.